Folks, welcome back after half term. So today, can you work out from this, what are we looking at? So here we have a car, we have some factories, we have production of gases. This is telling us what our gas is doing. So the arrow here is suggesting it is being absorbed into the ocean. We are getting a change in color, and not only of the ocean but of the fish as well. So any ideas? Okay, well, we're going to look at sea acidification and we'll have a little recap on what that is, but our learning intention today is we're going to be using evidence to support or reject the hypothesis that rising atmospheric carbon dioxide levels impact ocean pH and that global carbon dioxide levels are rising. So we have different sets of data for each hypothesis, and you have to go through them and decide whether you accept the hypothesis or reject it, and you need to tell me the evidence that's going to go with that. So just a little bit of reminder on sea acidification. So carbon dioxide from the atmosphere can dissolve in water, and it's going to dissolve in our ocean, and when it does that, it's going to reduce the pH of the ocean. Now the good thing about that is we learned the last week before half term that if you're removing carbon dioxide, you're removing a greenhouse gas, and therefore global warming has to reduce. So that is a positive. But a con, or very much a negative, is that if the pH of the ocean decreases, well then coral reef and shellfish, they're not going to be able to reproduce, and that's going to have a knock-on effect on biodiversity in those particular habitats. And we're going to investigate this more today, or use our acidification in the context of shellfish reproduction. So I'm going to play you this.
We're cousins. Our dads are Bill Taylor and Paul Taylor, and they run Taylor Shellfish.
And I'm Brittany Taylor, and this is Deani Taylor.
That too.
And we're the fifth generation of our family to work for our family business. I really take pride in the fact that our company is part of a big community, and it's very family-like. We have many families, not only mine, but many other families that have their whole families that work for us.
The ocean is so acidic that it is dissolving the shell of our baby oysters. Our farm is what has kept this family together. It's our glue. I can't imagine it would be devastating to lose that, such a big part of our history. When we started farming oysters over 100 years ago, we relied on the natural reproduction of oysters in the bay to occur in order to get our oysters. But as the industry has changed, we started cultivating our own oyster larvae, our own baby oysters. So when we started doing that, we needed something like our hatchery, which is kind of like a greenhouse where you can raise up the baby shellfish and the baby oysters to get big enough so that we can go and plant them on our beaches.
It took us a while to figure out what was happening in our hatcheries relating to ocean acidification, just because there's so many different things that can happen to make sea not survive. One of the things the hatcheries realized was that the clams and oysters were having problems forming their shell. So that made them look at the pH levels, because that's kind of accounts for it. Shellfish is very vulnerable when it's first being created, and it's the acidity in the water that makes it hard for them to form their shells.
So when it reaches the baby oysters in the first few days of life, that acidic water actually will dissolve the shell, which is calcium, and if they don't make it through the first few weeks of its life, when it's being affected by ocean acidification, then we have no oysters to plant on our beach. So it's something that we truly experience and deal with on a day-to-day basis. It's not something that's going to happen potentially in 5 or 10 years. Along the coast of Oregon, there's a specific function called upwelling, where deeper water is coming up towards the surface. And it's that deeper water that is the acidic water. We don't know how bad ocean acidification is going to get. We're just starting to experience the consequences of it. What we're experiencing here in the Puget Sound is what other people will be experiencing not too long in the future.
I definitely want to be able to pass on our business onto the next generation.
Yeah, it'd be fun to share that experience with the next generation, like our dads shared with us.
Okay, so there you have it. A real impact on pH of the ocean. It could wipe out a whole industry very, very quickly. So you have worksheet data. I've put this into OneNote for you. So if you want to type on over it in text boxes, you can, or if you want to write out the answers. So you've got to give it the right headers if you're going to write it out. So this is the first infographic that we're going to use, and it has pieces of information in it, and you have to come up with 3 pieces of information that the data tells you. So the first piece of information that we're using is the fact we're going from pH 8.2 in pre-industrial times to pH 8.1 in 2013, and it's telling me that the pH has gone from 8.2 to 8.1 and that the pH of the oceans in this example is decreasing. So find 3 pieces of information and you're going to write it in the table below. This one, I'm going to go through with this one for you. Now you will have some pieces of information because this is the first infographic over here. So you will have some pieces of information from this, but I'm going to explain to you this part over here. So the hypothesis is that rising atmospheric carbon dioxide levels impact ocean pH. So we've got to figure out, is that true or false? So you have your infographic 1, and I know now this is quite small on my screen, so hopefully it's bigger on yours. So what you are going to be trying to doing in this is select data relevant to the hypothesis, whether it supports it or rejects it, but just that it's relevant to it. So I'm going to just explain the chemistry of ocean acidification to you as simply as I can. And it's this little paragraph up here, and it goes with this diagram that's down here. So what we have is we have carbon dioxide in our atmosphere, up here in our little cloud. It is going to dissolve in water. So this is the carbon dioxide reacting with the water, and you have these arrows here. And what these arrows tell a chemist is, if the arrow is really, really big, then that's what's happening the majority of the time. So once carbon dioxide mixes with water, there is very little of it going back into the atmosphere. Now, when carbon dioxide, so that's this sentence up here, we have atmospheric carbon dioxide dissolving in seawater, and when it does that, it produces carbonic acid. So our rainwater is naturally acidic, but seawater will dissolve carbon dioxide, so it will have carbonic acid inside in it. So as again we can see from the arrow, once carbon dioxide gets into water, the big arrow is it's going to make loads and loads of carbonic acid. Now we have not looked at acids and bases. We've looked at them in terms of they are sour and that their pH is less than 7, but actually in something that's acidic, it is H plus ions that make something acidic. So the more H plus you have, the lower your pH. So you're down at the pH 1 or 2 if you have buckets and buckets of H plus. So what happens is your acid kind of falls apart, and it falls apart to this H plus thing that's here. So these are our acid ions that are going to be in our water. So up here they talk this word dissociation, and it's just a real posh way of saying they fall apart. So carbonic acid dissociates into this acidic portion, and this thing over here is called hydrogen carbonate. Now, just as I suppose an extra piece of information that you need to know. So we have our carbon dioxide dissolving in our water down here. We have it making the carbonic acid. The carbonic acid falls apart and it forms the H plus ions that are in the water. Just the other thing that you have to recognize in terms of the salinity is down here. This thing is called calcium carbonate, and it's essentially all shellfish have calcium carbonate in them. So the oysters and the clams that they were talking about, periwinkles, they would have calcium carbonate. And calcium carbonate itself can react with carbon dioxide and water that will be in our atmosphere. And when it does that, it makes this thing here, the hydrogen carbonate. And if that means that that is getting made, that means that there is no calcium carbonate for the shellfish to use. And that's the big issue, because in reality this scenario up here is the one that's existing big time once carbon dioxide is dissolving. So not only is the carbon dioxide contributing to making protons, but actually here the protons and the carbonate are combining to make you this hydrogen carbonate. So it's like this big circular thing that's ongoing. So once you have the carbon dioxide in your water, you're making your carbonate, but you're also using up calcium carbonate that fish or that shellfish can no longer use now to make their shells. So we go back to our hypothesis up here at the top. Rising atmospheric carbon dioxide levels impact ocean pH. So now you have some data or some evidence here in this middle section to help you. And if you want to have a read of the effects of ocean acidification, you can. But whatever pieces of data you use, you need to relate it back to this hypothesis. Now you can use one of your pieces of data here from your info 1, I will accept that, and there are at least 3 other pieces of data from this infographic. So have a good read and just keep relating it back to your hypothesis. Now in the next little part, you are going to put your data from your infographic 2, you're going to put your things that you found in here into your spaces here on the next activity, and you're going to tell me what this data provides evidence for what. So you're interpreting your data essentially, and in the space below explain how the evidence supports or rejects the hypothesis. And again, the hypothesis is this one up here. So if you think it supports it, it's not enough to say it supports it, you have to tell me how. How is it showing you? So give me some science to go with it. Can't be generic rubbish. Okay, we're preparing, we're going to do possibly CBA before the end of the year. That's going to count towards your junior cycle, so you can't give me rubbish. Now I've been giving you feedback all along, and you need to be taking it on board and actually using it. Now the next thing that we're going to look at are 2 separate graphs. So we're seeing now all the time that graphs no longer are this beautiful straight line like this. These graphs are kind of funky. So over here in figure 1, we now have atmospheric CO2 at 2 different sites. The blue is Seattle and the green is Washington State, and they're collected on different dates. And what I want for you to do when you look at any graph that's giving you data over years is I want you to look at what happens within a year. So if you go from 2007 here to 2008, what's happening to the curve of the line, what's happening to the CO2, and then you look at what's the overall curve. So if I pick this point every time on your graph, so if I pick this point, what is my CO2 levels like on green? What are my CO2 levels like on blue? So you're finding the trend. Similarly over here for figure 2, this is data for global atmospheric carbon dioxide taken from 173 sites. So again, you look at a point for what's going on within a year, and you should see the same trend over both graphs, and also then what's going on if I now compare the same point over many years. Okay, now in terms of what you're being asked to do, the hypothesis is now changed. the hypothesis is now global atmospheric carbon dioxide levels are rising over time. So now you're looking at your graphs, and you're looking at the data, and you're looking at under the context of the what happens within a year. So you might have a piece of selected data here, and what happens from 2016 to 2014. What's the data, the evidence that it provides? Does it support or reject your hypothesis? And down here at the very bottom we have this other question: what other evidence might you need? So you need to have a think about this now, and what else would you need to have to confirm that. So the only thing I would say here is that we have only 2 places. The next graph that we're going to look at has more places, but what other evidence might you need now to do this? So again, we're looking at our second curve now, and in our space below, explain the evidence that supports or rejects the hypothesis. So using that graph and the information from it, what is the evidence that supports or rejects your hypothesis? So that's our within class lesson stuff. As I say, we're building up to do a CBA on this. So you need to do some further research to find evidence on your hypothesis. And we're looking at the idea that raising our atmospheric carbon dioxide levels will impact our ocean pH. So we're going to look at it as kind of like a hear no evil, see no evil, speak no evil type scenario. So if I ask you to go and research, everyone will go and they'll find me web links and web pages and blah, 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 blah. But that's only one way, because that's for somebody that's really good at reading. So brilliant. But now then I want you to go and find me a YouTube or a TED Talk clip, and that will be for somebody that their skill set is going to be that they are capable of really good listening. And then finally, I want you to find an image or a graph that's going to help you in terms of evidence for this hypothesis. And again, that's going to be for somebody that's actually really good at looking at data and seeing trends from it. And these are skills that you're going to be able to need to use for your third CBA. Or your CBA that we would do in year 3, but we're going to do it in year 2 now. I'm showing you this because this is what we're coming up to do on Thursday. So you are going to be a press regulator. You are going to be looking at the information that's been given in this particular section of an article, and you have to decide whether the public has been misinformed, and you have to give evidence as to that decision. Okay, and I'm just going to show you this. So we have done this before where we had, and I'm showing you this part because this may be the part that you will recognize the most, where we have all of these sources of evidence, and you come up with your pros and your cons, and what's your position and why, and what are the findings that support. So if you go back in and look at the handouts that I've given you, I don't think we've done any this academic year, but maybe we did, but we're going to be using a version of this format, and this is going to help you to set up for your CBA. It's called CBA 2, but we're going to have the practice at it, and it's worth 10% of your junior cycle next year. We may be doing it early. We're going to wait and see and find out. So I am on, so the last couple of slides, so this is just an FYI. You are going to use what we've done today, what the things you found out today, plus your evidence. Now, it's not that you're just finding me the web link. You are going to find me a web link, and you're going to have your evidence from it. So for each of these, I want the evidence that supports or rejects your hypothesis. Okay, so there's a little bit of work in it, but I am on Zoom should you need me. Talk soon.